In this video, we'll generate the trendline polynomial of the Gaussian integral using ERFC and the ERF function or the error function. Begin with the Gaussian integral, which is the summation of a times x to the power 2n plus 1, where the value of the coefficient a is negative 1 to the power n plus k, and all over n factorial times 2n plus 1. Here, the value of n will be from 0 to infinity. So in this case, we can go as far as 16, which is good enough. And the value of k will be data validation, list of items, 0 if it is ERF function, the error function, 1 if it is the ERFC function or the complementary error function, and save. So we have two values, the ERF function and the complementary function. Now we can generate the Taylor-Maclaurin series sum, which is array formula, series sum of the x values raised to the power 2n plus 1, where 2n plus 1 starts from 1. Then the next will be 3, 5, 7, 9, so the increment is 2. And the coefficient will be this range, which is the A column. Now we can continue calculating the coefficient. So array formula, minus 1 raised to the power, the quantity n plus k. All over, two quantities there. That's the first one is factorial n. Factorial of n. The second one will be 2n plus 1 times the quantity. That's 2n plus 1. So 2 times n plus 1. Then enter. So if it is the ERF function, here we have the trendline polynomial and the trend line, which is the ERF function. Next, we calculate this regression coefficient using LINEST. We begin with the LINEST matrix, which is equal to transpose from 0 to 8. And to complete the LINEST matrix, array formula of the x values raised to the power 0 to 8. Now we calculate LINEST, which is equal to LINEST. We should be in the middle here, which is equal to LINEST data y and data x. So here we have the regression coefficients. So x to the 0, that's 0, 0.997 for x, 0 for x squared, minus 0.313 for x cubed, 0 for x to the 4th, minus 6.0696 x to the 5th, 0 x to the 6th, minus 6.54 times 10 to the minus 3 of x to the 8th, 7, and 0 x to the 8th. If we change that to 1, which is the error function, the complementary error function, we have 0 minus 0.997, 0 for x squared, minus plus 0.313x cubed, 0 x to the 4th, minus 0.0696 x to the 6th, x to the 5th, 0 for x to the 6th, and 6.54 times 10 to the minus 3 x to the 7th, 0 x to the 8th. Next, we continue with the error function, which is equal to, we begin with the error function, array formula, ERF of the x values. And multiply square root of pi times 0.5. So that's times square root of pi Enter. Finally, 0.5. 0.5 times 0. That's the error function. Now for the complementary error function, this will be array formula ERFC of the x values. Next, we subtract -1. So -1. Enter. And finally, multiply by 0.5 square root of pi. So times, start with 0.5 and then square root of pi times square root of pi. And this should be multiplied to ERFC. Now they're all in the same trend line and their trend line equations match. We complete the calculation of the polynomial regression coefficients. So this will be LINEST, data y, and data x. This is for the ERF function. And LINEST also, data y, and data x for the complementary ERF function. So we compare this with our trend line. So k equals 0. These data sets are the same, meaning the expansion approximates the complementary error function. If it is 1, our expansion approximates the error function. And the trend line also, the polynomial regression coefficients also match. At k equals 0, the red is on the blue. The expansion approximates the error function. If k equals 1, the expansion approximates the complementary error function. This completes the use of ERFC, ERF, Taylor Maclaurin SERIESSUM, and LINEST Polynomial Regression to generate the dataset and trend line of the Gaussian integral.